So an antiderivative, like the name implies, undoes a derivative. Or when I think about antiderivatives, I often kind of think about them in the same way I think about inverse functions. Here's what I mean. I'm going to go inverse straight because that's kind of the most typical example. So if I said I want to find the inverse sine of 1/2, when I read that, I really am reading it as I want to find the angle. If I took sine of that angle, I would get 1/2. If I'm thinking of inverse sine of 1/2 equal to x, I'm thinking of that equivalently as sine of x is equal to 1/2. So I'm trying to find the thing that undoes the thing I'm actually doing, right? I know sine of an angle equals 1/2. I know the angle is pi over 6. So I know the inverse sine of 1/2 is equal to pi over 6 because sine of pi over 6 is equal to 1/2. Well, the same sort of relationship is true with functions and, with derivatives and antiderivatives. They kind of undo each other. So if I want to say, and typically the notation we use for this is capital function letters. So if I say that my function, like f of x, is equal to, I'm going to pick something easy, like 5x to the 6, that's not what I meant to do. 5x to the 4th is what I meant to do. And I say, okay, what's the antiderivative? Well, I'm looking for the function, and if I take the derivative of it, I get 5x to the 4th. Well, I know what that function is. That function is x to the 5th. And hold on for a minute if you have to. I know I'm not saying the whole thing here, just a sec. Because we know the derivative of x to the 5th is 5x to the 4th. So when I say I want to find the antiderivative of a function, the words I'm really hearing in my head are find the function that if you took the derivative of it, you would get the thing you're starting with. Find the function that if you took the derivative of it, you would get 5x to the 4th. Oh, I know what that is. It's x to the 5th. Because I know when I take the derivative of x to the 5th, the coefficient comes down in front, and the power is 1 less than it was before. Now, a lot of you are probably thinking, James, what about plus c? And you're totally right. Technically, my function could have been x to the 5th, but it also could have been x to the 5th plus 2, or x to the 5th minus 17, or x to the 5th plus any constant. So when you find an antiderivative, you're actually finding a whole family of antiderivatives. So what we actually typically write is our antiderivative is whatever your function is with the variable x, and then you tack on a plus a constant. Because the derivative of x to the 5th is 5x to the 4th, and the derivative of c is 0. So whenever you're finding a general antiderivative, you're always going to tack on a plus c there. All right, so let's look at some more examples. Now, for powers of x, we actually already know what to do, well, except for one. Although we know that. Let's see. So here's the general, I call it the anti-power rule, which always feels like I'm saying something vaguely not great, but it's right. I'm just talking about the anti-power rule. So the anti-power rule so we know that the derivative, so we know that the derivative of x to the n is equal to n times x to the minus 1. The kind of neat thing about antiderivatives is you're kind of undoing what the derivative does. It's easiest to say for this one, other ones it's less easy. So if the derivative multiplies by the power and then subtracts 1 from the power, the antiderivative undoes that in the opposite order. So first it adds 1 to the new power, or to the old power, and then it divides by the new power to undo the multiplying. So if my function f of x is x to the n, then my antiderivative is x to the n plus 1 divided by n plus 1. Let's see. And you know what's great about antiderivatives is as long as you know how to take derivatives, you know how to check to see if you're right. Let's check. So if I want to find capital F prime, let's see, I'm going to rewrite this as 1 over n plus 1 times x to the n plus 1 plus c. Remembering that n is just a number. So when you take the derivative of a constant times a function, the constant hangs out. And the derivative of x to a power, well, we know the derivative of x to a power is that power, which is n plus 1 in this case, times x to our power minus 1. And then the derivative of c is 0. Well, look, the n plus 1's cancel, and n plus 1 minus 1 is just x to the n. So the derivative of this is that. So the antiderivative of this is that. In fact, that's worth writing down. In kind of a silly way, but right, from here to here, if you go from here to here, you're taking the antiderivative. And from here back to there, you're taking the derivative. That is always true. In fact, that's the whole crux of the fundamental theorem of calculus, which you'll learn next quarter, is that the derivative and the antiderivative undo each other. Now, I will mention, because it's important, there is a value of n that this doesn't work for. Can anyone think of a value of n that might make this a big old problem if you divide it by n plus 1?
-1.
Right. So this anti-power rule is true except for when n is equal to -1. So that begs the question, well, what if n is equal to -1? What if your function f of x is x to the -1, better known as 1 over x? Do we know a function? And so, right, I'm going to ask the question, what's the antiderivative of 1 over x? Or better said in my head, what's the function whose derivative is 1 over x?
Natural log of x.
And that is mostly right. Well, mostly right. Yeah. Natural log of x plus c. However, there is actually, it's actually not exactly right. It's not that it's not right, it's just that it's not as right as it could be. And I don't know if your teachers have said this or not, but you're definitely going to see it next quarter. So the problem with the natural log of x, wow, the problem is I can't put this cap on my pen. The problem here is that we would like the antiderivative to have at least as big a domain as the function. And here, the domain is everything but 0. And here the domain is significantly less. It's everything that's positive. But the domain of the antiderivative should kind of have all of the domain of the function. Right? You shouldn't anti-differentiate, you kind of get less domain. It's weird. And the thing is, we actually don't. It's just that we're not looking at this as fully as possible. So it's actually kind of interesting. Here's 1 over x. Yeah, here's 1 over x. There's the graph of 1 over x. And we know that at least over here, the derivative is the derivative is the natural log of x. So right here, the slope is very negative. Right here, the derivative is very negative. Right here, the slope is, still negative. It's actually -1 right there. Right? Or, here it is. And right here, the derivative is, the value is 1. And so on, right? So as, I feel like I've done something idiotic here. Have I done something idiotic? I'm getting, When I'm getting idiotic is I flipped the function in the derivative. I said natural log of x was the function. Wow, whoa. Let's back that up. Sorry, I was getting things very, very, very wrong. Let's try this again. Let's say that our function f of x is 1 over x, and our antiderivative is the natural log of x. So if I take the derivative of this, it's equal to that. So now let's say it the right way. The derivative of this right here is very positive. The derivative is very positive. Here the derivative is still positive, but less so. Okay, this is positive but less so. Even still positive, positive but less so. Now here's what's kind of interesting, I think. If this is the derivative, the values are super positive and then less positive. Over here, if this was the derivative, well, the function it's the derivative of, the values are very negative over here, less negative over here. Can I find the function that's very negative over here and less negative over here? Well, yeah. Sorry, whose derivative is very negative over here and less negative over here? Yeah, it looks like this. And there's symmetry because of the fact that this and this essentially are symmetric. They're actually odd functions. This is an odd function, they're symmetric. So kind of beating around the bush here. Here's what I really want to say. If your function is 1 over x, the antiderivative, the better choice for the antiderivative is actually the natural log of the absolute value of x. It's the natural log of x when x is positive. It's the natural log of negative x when x is negative. And its derivative is this. This is kind of the cool part. So if you write this, if you write the natural log of the absolute value of x as a piecewise function, which is the natural log of x if x is positive, and the natural log of negative x if x is negative. What's the derivative of the natural log of x? I know you guys know. The derivative of the natural log of x is 1 over x. What's the derivative of the natural log of negative x? Well, the derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff when x is less than 0. But look, those are the same. So the derivative of the natural log of the absolute value of x is 1 over x if x is less than 0, and it's 1 over x if x is bigger than 0. So it's just 1 over x as long as x isn't equal to 0. Okay then, right? If I'm trying to find the antiderivative of 1 over x, it's the function whose derivative is equal to 1 over x. And I might as well pick the one that has the larger domain, the domain that's actually the same as 1 over x. So while you might say that the antiderivative of 1 over x is the natural log of x, the more correct answer is that the antiderivative is the natural log of the absolute value of x plus c. Something to be aware of. It definitely comes up next quarter. All right. So here's the thing to know about antiderivatives at this juncture. Any function you know the derivative of, you know the antiderivative of that derivative. Like all your trig functions. So for example, I'm going to write it this way. If my function is cosine of x, what's the antiderivative of cosine? Well, whose derivative is cosine? Positive sine. This pen is not doing it for me. Let's try this other orange pen instead. If your function were sine, who has a derivative that's equal to sine? Negative cosine. Yeah. So the nice thing about sine and cosine is their derivatives and their antiderivatives are just actually opposite sides of each other. So the derivative of sine is cosine. The antiderivative of sine is negative cosine. The derivative of cosine is sine. The antiderivative of cosine is sine. The derivative of cosine is negative sine. Other trig functions, a little more work, right? If you say, what's the antiderivative of, I don't know, secant squared of x, I know a function whose derivative is secant squared of x. It is tangent of x plus c. So we're really just kind of pointing out that if you have functions, if you have a known derivative, you know the antiderivative. Here's one that might not look quite as normal. What if your function was 1 over 1 plus x squared? What's the antiderivative? Or what's the function whose derivative is 1 over 1 plus x squared? It's not a natural log. It's an inverse trig function. Right? We know the derivative of the arctangent of x, or the inverse tangent of x, is 1 over 1 plus x squared. So we know the antiderivative of 1 over 1 plus x squared is the arctangent of x plus c. And or I guess if you wanted to be silly about it, you could say negative arc cotangent of x, but we don't usually do that. In a similar way, if you had 1 over the square root of 1 minus x squared, let's make it negative. So there are two correct answers here. One of them is the real correct answer. Typically, I would say, well, I know the derivative of arc sine of x is 1 over the square root of 1 minus x squared. So the derivative of negative, so the antiderivative of negative 1 over the square root of 1 minus x squared is the negative arc sine of x plus c. It would be equally valid to say that the answer is the positive arc, that's spell arc the right way, cosine of x plus c. If you recall, the derivative of arc cosine of x is negative 1 over the square root of 1 minus x squared. And the derivative of negative arc sine of x is negative 1 over the square root of 1 minus x squared. So either one of these is correct. Usually we default to the arc trig functions that are not arc co-functions. So we typically always try to use arc sine, arc tangent, and arc secant if we are faced with an arc trig function. Yeah. Okay, let me zoom over here for a second. Ooh, yeah, those are some good questions. So let's look at this question. Yeah. Sometimes people like to throw in some initial conditions. I had a good question somewhere that I would really like. No, you disappeared from my brain. Fine. So let's say we have this. I am given that. Sure. Sometimes, so instead of writing a little f and big F, sometimes people just say the derivative is this. So given f prime of x is equal to, yeah, sure, let's make it fun. X squared plus e to the x plus cosine of x. Find the original function, the antiderivative, given that f of 0 is equal to 8. Let's make that 8/3. Let's make that 7/3. I don't know if that's going to really make it any nicer, but there's a chance of that being slightly nicer. 7/3, sorry, you could like, yeah, sure, 7/3. Why not? 7/3. Okay, cool. So what this part really means when you're given f of 0 is something, or f of 1 is something, right, some initial condition, these words mean we have to solve for c. That is the hidden meaning behind it. You have to figure out what your constant actually is. But first, we have to antidifferentiate. So f of x is the antiderivative of x to a power is x to the power plus 1 divided by the power plus 2. or x cubed over 3. Everyone's favorite function to anti-differentiate. What's the antiderivative of e to the x? Oh, it's e to the x. Right? It's kind of the best. And then what's the antiderivative of cosine of x? It is sine of x plus c. So then, after we find the general antiderivative, which is what this is usually called. When you have the function where it's plus c, we call that the general antiderivative of this function here. Now I want to find the particular solution. So I'm going to plug in 0. And f of 0 is going to be, I don't know why I'm just so, I got caught up with the 7/3 like this was going to make a difference. Oh well, that's fine. So f of 0 is 0 over 3 plus e to the 0, which is 1, plus sine of 0, which is 0, plus c. And this is equal to 7/3. So 0 plus 1 plus 0 plus c equals 7/3. So c equals 7/3 minus 1, which is 4/3. And technically, we then need to go back and actually write what the function f of x is. So f of x is actually equal to, so the answer here is what the function is. It's x to the 3rd over 3 plus e to the x plus sine of x plus 4/3. That's our final answer there. I had another, I know I had another fine. Sure, let me. Let me make up something real quick on the other side here, just so I can think of it for 1 second. Sorry, sometimes it's hard to come up with nice problems. I don't want to be so lame. Let's do that. And sure, that'll be super exciting, maybe. Except I'm totally looking at the wrong thing. Okay. Sure, that'll be interesting. So let's say we are given this. We are given that the second derivative of the function, f del prime of x, is equal to 12x squared plus 2. And, right, am I doing something really, really dumb? I don't think so. And we also are given these to be derivatives. The f of 1 equals f of negative 1 equals 3. Is that right? Yeah, that's right. Okay. So let's do this one. This is going to be extra interesting. Sorry, let me do this here. So if I want to find, oh, and the question is to find this. Question is this pen still worth using? And the answer is probably no. So first I'm going to anti-differentiate this. So the antiderivative of the second derivative is the first derivative. And again, I'm just using the reverse or anti-polynomial here. So the antiderivative of 12x squared is going to be 12x cubed over 3. What's the antiderivative of 2? Thank you, Caitlin. Yes, exactly. And that's always true for a constant. When you anti-differentiate a constant, it's just that constant times x. Technically, if you wanted to, you could imagine you were using the anti-power rule here. You could say, oh, I have 2 times x to the 0, and when I anti-differentiate that, I get 2 times x to the first divided by 1. I don't think you should do it that way, but you could if that made sense to you. I just want to think about, oh, well, I'm trying to find the thing, if I differentiate it, I get 2. Well, the derivative, if the derivative is 2, that means the slope is always 2, which means I have a line that is y equals 2x. All right, and then I'm going to simplify this, especially if I'm going to anti-differentiate again. It really is worthwhile to simplify. That's going to be 4x cubed plus 2x plus c. And if someone had told me what f prime of 0 was, or f prime of something was, I could solve for c right now. But they didn't, so I can't. So I'm going to anti-differentiate again. So the antiderivative of 4x cubed is going to be 4x to the 4th over 4, or just x to the 4th. The antiderivative of 2x is going to be 2x squared over 2, which is just x squared. Okay, everyone should be able to answer this. If the antiderivative of 2 is 2x, what's the antiderivative of c? Replace the 2 with the c, and you get cx. Yeah, whenever you anti-differentiate a constant, even if you don't know what the constant is, you still get that constant times x. But then we have to add on another constant, which is not the same as that constant necessarily. So yeah, every time you anti-differentiate, you have to add on a new constant. It is not necessarily the same as the previous constant. Right, and now we're going to simplify this and use our two initial values to figure out what c and d are. So f of x is x to the 4th plus x squared plus cx plus c. And I think all my blue pens are just dead. So I plug in 1, let's see what I get. F of 1, and that's a good blue pen, is 1 plus c plus d, and it's equal to 3. Okay. And then f of negative 1 is 1 plus 1 minus c plus d, and it's equal to 3. And then you can solve this whatever way you want. You could isolate d here and then plug it in here. For this problem, the easiest way to do it might be just to actually add this equation to this equation. What do I mean by that? I mean, I'm out of the room, this is over here. What I mean is you could totally take 1 plus 1 minus c plus d equal to 3, and 1 plus 1 plus c plus d equal to 3. And you could actually either add or subtract these equations. If you add the equations, the c's will cancel. If you do this equation minus this equation, the d's will cancel. I think it's easier to add the equations anytime you have the choice. So I'm going to add this equation plus this equation and get 2 plus 2, not, I mean, you could just say, right, this is 4. No c's plus 2d equal to 6. So 2d equals 6 minus 4. And d equals 1. And then I could go back and I could plug in for d, and 1 plus 1 minus c plus 1 equals 3. So 3 minus c equals 3, so c has to equal 0. And there's a word I'm looking for. That confirms that is not the word I'm looking for. That makes sense with what is happening over here. And we can see that also true over here. C has to be 0 because d is 1. 1 plus 1 plus 0 plus 1 equals 3. So our final answer is that our function f of x is x to the 4th plus x squared plus 0x. I'm not even going to write that term, plus 1. Okay. Let me ask you 2 more questions. Let me give you 1 or 2 more antiderivative questions. So I am always a big fan of asking questions like this on a test. Oh yeah, that's a good question too. We'll do that as well. Let's do, sorry, I lost my, okay. So let me ask you guys this question. If f of x is equal to 2x times cosine of x, is the antiderivative equal to x squared times sine of x? So the point of this problem is not to try and anti-differentiate that, because we don't yet have the tools to anti-differentiate something like this. So if I'm asking, does a function have a certain antiderivative, the question I'm really asking is, does the derivative of the antiderivative equal f of x? And I suppose I should have a plus c over here. What do you guys think? Yes or no? Does the derivative of that equal that? Definitely not, because of the product rule, right? So the answer is for sure no. The derivative of this is going to be 2x times sine of x plus x squared times cosine of x. Let me ask another similar question that I don't know if I have the answer to off the top of my head. Let's see, I guess I've got, yeah, not you. Sure. Yeah, let me ask this. So, is the antiderivative of f of x equal to x cosine of x? Equal to f of x equal to x sine of x plus cosine of x plus c. And again, the point of this question is not to try to actually find the antiderivative of this. The point is that if the antiderivative of this is that, then the derivative of that is this. So if someone ever asks you, is the antiderivative of thing this other thing, take the derivative of the other thing and see if you get the function you're supposed to start with. So let's find the derivative of capital F, right? Or the derivative of capital F, which is product rule. 1 times sine of x plus x times cosine of x plus the derivative of cosine is negative sine of x plus the derivative of c is 0. And look, the signs cancel out. And you get x cosine x, which is equal to f of x. Check. And maybe, no, just check. Check, it works. This is, so yes, the answer is yes. The antiderivative of little f of x equal to x cosine of x is capital F of x equal to x sine of x plus cosine of x. Let me give you one more antiderivative style problem, and then I guess I think we'll look at the spring 07 review and see if there's any particular problems that you guys want to look at. So, yeah, where am I in here? Oh yeah, what's the antiderivative of this function? F of x equal to, let's see what I got here. 4 plus 6x minus 7x squared over 2 square roots of x. And so this thing here, while it might look complicated at first, we can simplify into a thing that's just a bunch of sums or differences of powers of x. So since I've got a single term, I can rewrite the function as 4 over 2x to the 1 half plus 6x over x to the 1 half, 2x to the 1 half, minus 7x squared over x to the 2x to the 1 half, which I can then simplify further as 2x to the negative 1 half plus 3x to the positive 1 half, right? I'm subtracting the powers and doing x to the 1 minus 1 half, or x to the 1 divided by x to the 1 half. Minus 7 halves x to the 3 halves. And now these are all just powers of x. We can totally differentiate this thing. So the antiderivative is going to be Well, again, I'm just going to use that reverse power one. Unless one of my powers is negative. But none of my powers are negative one, so I don't have to use the reverse power rule. Or I mean, I don't have to use the natural log thing. So I'm just going to add one to the power and that new power. And you might want to do this in 2 steps, right? So I can really just write this as -1/2 plus 1 over -1/2 plus 1. You are obviously welcome to do more simplifying than I'm just doing this one step here. This is going to be, what's 6 over 2 is 3. And, oh, sorry, which I did already here. But then my new power is going to be something that has x to the 1/2 plus 1 divided by 1/2 plus 1. And then here I'm going to get -7/2 times x to the 3/2 plus 1 over 3/2 plus 1. You are going to want to get relatively proficient at doing this, adding 1 to a power and dividing by the new power, because you're going to do it a lot next week. So -1/2 plus 1 is 1/2. So I'm going to get 2 times x to the 1/2. And dividing by 1/2 is the same as multiplying by the reciprocal. Here, I'm going to get 3 times x to the 1/2 plus 1 is 3/2. Dividing by 3/2 is like multiplying by 2/3. Here, I'm going to get -7/2 times x to the 3/2 plus 1 is 5/2. Dividing by 5/2 is like multiplying by 2/5. And then we should simplify all these coefficients. This is 4 times x to the 1/2 plus 2 times x to the 3/2 minus the 2's cancel and you get 7/5 times x to the 5/2 plus c. So when you see some sort of fractional looking thing like this that you're supposed to anti-differentiate, the idea is that you want to break it up into many simple things that you can actually use the anti-power rule on. So the limit as x goes to 0. Oh, also, you guys probably can't actually see them anymore. So if you want to see them and if you want to try and go look at them while I'm doing problems, you can go find them in the module section of Canvas. So they're there. So this problem is the limit as x goes to 0 of the inverse tangent of x minus x over the inverse sine of x also minus x. This is going to be a little bit gross. I feel like it's new pen time. I deserve a new pen. You know, what a gift to myself. A brand new pen. It's Christmas time, right? You know, I deserve a new, nice, shiny, nice writing pen. And you do too. You deserve to see things written in a nice new pen. Okay. So clearly we're going to be using L'Hopital's rule because this is a 0 over 0. Inverse tangent of 0 is 0. Inverse sine of 0 is 0. 0 minus 0 over 0 minus 0. So using L'Hopital's rule, because we have a 0 over 0, we can take the derivative of the top and the derivative of the bottom. Okay, the derivative of the inverse tangent of x is 1 over 1 plus x squared. Derivative of x is 1. Derivative of sine is 1 over the square root of 1 minus x squared minus 1. Okay, if you plug in 0, guess what? You still have a 0 over 0 type. How exciting. Yeah, how exciting. So we probably have to use L'Hopital's rule again. The question I'm asking myself in my head is, do I want to try and simplify this at all before I use L'Hopital's rule again? I honestly don't know. Yeah, I feel like it's going to be terrible. Let's go with not simplifying. Except, well, I'm going to do one thing. I don't really want to use the quotient rule, so I'm going to rewrite this. Limit as x goes to 0. And by quotient rule, I mean the quotient rule for this part and for this part when you use L'Hopital's rule. I'm going to write this as 1 plus x squared to the minus 1, and this as 1 minus x squared to the minus 1/2. I think that's going to be probably the least terrible way to do this. So let's use L'Hopital's rule again. The limit as x goes to 0 of So the derivative of the top is going to be negative 1 times 1 plus x squared to the negative 2 times 2x. Oh, man. I was worried we're going to have 0 over 0. And we would if we're not careful. The derivative of the bottom is going to be negative 1/2 times 1 minus x squared to the negative 3/2 times negative 2x. And if we just plug in as is, you might think we have to use a 0 over 0 again, or a L'Hopital's rule again. Because you plug in 0, negative 1 times 1 to any power is 1 times 0 over negative 1/2 times 1 to any power is 1 times 0, which is still a 0 over 0. But we can cancel some stuff, right? Those 2's cancel, and more importantly, those x's for sure cancel out. If you wanted to, just to see what this looks like, you could rewrite this as a limit as x goes to 0 of this top part. You could write as negative 2x over 1 plus x squared squared. This bottom part, you could write as negative 1/2 times negative 2x over 1 minus x squared to the 3/2. But really the important thing to recognize here is that this negative 2x and this negative 2x will cancel out. And we could, and then really, I mean, you could simplify this further, but why bother? Let's just plug in 0 and get 1 over 1 plus 0 is 1 over negative 1/2 times 1 over 1. So I end up with 1 over negative 1/2, which is negative 2. That's cool. I was expecting to get 0. It's always cool for it to be when it comes out to be like not 0 or not infinity. I'm like, oh, that's interesting. So bizarrely, this top part is approaching 0 at a rate that is negative 2 times as fast as this bottom part. Interesting.
I got a positive 2. Did I miss a negative?
So did I make a mistake? Let me double check here. So I feel like I'm supposed to be getting a negative because, so let's check my derivative. I have a negative 1 times 1 plus x squared to the negative 2 times a positive 2x. And on the bottom, I have a negative 1/2 times a 1 minus x squared to the negative 3/2 times a negative 2x. So I'm pretty sure it's going to be negative because I can see that the top has a negative sign overall, but the bottom has a negative times a negative, which is making me feel like I'm pretty sure it's supposed to be positive. No, but I can't see, I canceled the negative 2x on top with the negative 2x on the bottom. So that's why I don't think I have a negative on top.
So that the 1 plus x squared to the negative 2 is not a negative?
It's not.
Oh, okay.
Because when you plug in 0, what do you get?
1.
1 to the power.
Yeah.
Still 1.
Okay.
1 to the negative second is just 1 over 1 squared. So yeah, when you have 1 to any power, you do get 1. When you have negative 1 to a power, it can be either negative 1 or 1, depending on the odd or evenness of the power. Yeah, it is negative 2. Neat. I like neat problems like that. I mean, I like neat problems, like other things too. All right, let's look at the other limit problem that people specifically requested, which was problem 1D. Oh, this looks like a good one. The limit as x goes to infinity of 3x minus the square root of 9x squared minus 4x. And I will point out that this is an indeterminate form. This is an infinity minus infinity. This is going to infinity. And you might not be sure about this one here, right? This is, I guess technically this is also an infinity minus infinity. But here you can more reasonably justify that this thing inside the square root is going to positive infinity because you have a larger infinity minus a smaller infinity. Whereas this minus this, you can't really be sure which one's the larger one, but x squared is definitely much, much larger as x gets large. as 4x. Alternatively, if you don't like that explanation, you can write the insides here as x times 9x minus 4. And then you can definitely justify that as x goes to infinity, you get infinity times infinity, which is infinity. So this part is going to infinity. So we have the dreaded infinity minus infinity indeterminate form. And it is indeterminate. And I think our answer here is going to end up being like, I think it's going to be like 1/6. So the only thing we can really do here, which is something we've done before, although we might not remember it, I mean, not for this exactly, is we have to use the conjugate, right? The only way to kind of deal with something minus the square root or something plus the square root is to multiply by the conjugate. But you can't just multiply by the conjugate. You have to multiply by 1, which is the conjugate over the conjugate. So multiply by 3x plus the square root of 9x squared minus 4x over the same darn thing. All right, let's take a look. I don't do this anymore. So this is divided by 1. So the limit is x goes to infinity of 1 times that. So the denominator is just 3x plus the square root of 9x squared minus 4x. And then the top is going to be 3x times 3x, which is 9x squared, minus, the middle terms cancel, right? You get a minus this times 3x and a plus this times 3x. Those cancel out. And then you get a minus this times this, which is 9x squared minus 4x. And then, not surprisingly, the 9x squared and the minus 9x squared cancel out. So I have the limit as x goes to infinity of positive 4x, right, because the minus sign distributes, over 3x plus, I'm going to not write this down just yet because there's something I want to do to it. So I will point out that at this juncture, I have 4x over this. The highest power in the top is x to the first. And the highest power in the bottom is essentially x to the first. I've got an x to the first here, and I've got a square root of x squared there, which is acting like x to the 1. So I'm kind of viewing this as a rational function, where the highest power on top is x to the first, and the highest power on the bottom is x to the first. And if I can kind of deal with that, I could probably figure out what this limit is. The way to deal with that is to factor out an x from the square root, which means I have to pull out an x squared inside the square root. So I'm going to rewrite the insides of the square root as x squared times 9 minus 4 over x. You might be thinking, James, why don't you just use L'Hopital's rule like a sane person? And I would respond with, because L'Hopital's rule doesn't work here. I mean, it works in that you can use it, but the problem, well, I always say this, and then like sometimes it's actually not true. You might be able to use L'Hopital's rule here. Let's check. Let's see if L'Hopital's rule actually works. So instead of writing it like this, I'm going to write it as 4x over this stuff. And let's try using L'Hopital's rule just to see if maybe it works out. So if I use L'Hopital's rule here, I'm not convinced it's going to work. Let's see. Using L'Hopital's rule, the derivative of the top is just 4. The derivative of the bottom is going to be 3 plus the derivative of some stuff to the 1/2 is 1/2 times my stuff to the negative 1/2 times the derivative of my stuff, which is 18x minus 4. And here's why this is looking bad. If I simplify my denominator here, I've got a limit x to infinity. The top is 4. The denominator is 3 plus, I'm going to rewrite this whole thing as 18x minus 4 over 2 times the square root of 9x squared minus 4x. And although it's not exactly the same, I'm kind of getting back to the same terrible spot. This 18x minus 4 over 2 square root of 9x squared minus 4x is pretty similar to 4x over 3x plus the square root of 9x squared minus 4x. This kind of thing often ends up getting you in some sort of infinite loop, where if you want to use L'Hopital's rule again, you kind of you flip this over, or you multiply both sides by top and bottom by this denominator. So then you get 4 times 2 root 9x squared minus 4x over something gross on the bottom. And you just keep going back and forth, flipping this to the bottom, to the top, to the bottom, to the top, to the bottom, to the top, and you never actually get a result, which is kind of annoying. Instead, you actually have to do this problem by not using L'Hopital's rule. Sometimes L'Hopital's rule is just not the tool for the job. So here we are going to say the square root of x squared is equal to what? Square root of x squared?
Absolute value x.
Thank you. Yes. In this problem, it doesn't really matter because x is going to infinity. And since x is positive, the absolute value of x is just x. But it wouldn't surprise me if someone asked a question like this where x was going to negative infinity. And then the absolute value of x you'd have to replace with a negative x. So just be aware, weird things can happen. But yes, it's the absolute value of x, which in this problem is just x. And since I'm low on room, I'm going to do this next step kind of the lame teacher way, where I just like erase it and rewrite. I'm going to factor out an x from each of those terms. And then the x on top and the x on the bottom cancel. And now look what I've got. I've got the limit as x goes to infinity of 4 over 3 plus the square root of 9 minus 4 over x. And now I can actually evaluate it. 4 over x goes to 0. And then you get 4 over 3 plus the square root of 3 plus the square root of 9, which is 3. So you get 4 over 6. So I was off. I thought it was 1/6. It's 4/6. Interesting. So in this case, infinity minus infinity was 2/3. This infinity was 2/3 bigger than that infinity. It's not really what's exactly I should say, but it's kind of what's happening. Are there questions about what we've done here? Would anyone like to see any of the other limit problems before I look at problem 6 and or problem 12? All right. I mean, we can still go back to the limit problems, but those who spoke first get their questions answered first. The squeaky wheel gets the grease. All those lame sayings. Sometimes the squeaky wheel gets kicked out. I mean, not in my house. Like, you guys can be as squeaky as you want to be. I will happily try to address any and every question I'm able to get to. But let's look at problem 6. Use implicit differentiation to find the highest and the lowest points on the ellipse. X squared plus xy plus y squared equal to 27. So the question has to find the highest and lowest points. The highest and lowest points are going to be where the derivative is equal to 0. Especially if you're on an ellipse, right? If it's an ellipse, maybe it's weirdly oriented, which I think this one is. So there's some highest point here. There's some lowest point here. We do expect there only to be one of each because the problem says it's an ellipse, right? If I didn't actually know what the shape was, I might not know what to expect. But here I'm trying to find where y prime is equal to 0. Okay. And I will admit, I'm not exactly sure how to do this problem. I think I know what to do, but it might take a little bit of doing, which is, right. So let's talk about, I want to find where the derivative is equal to 0. So let's find the derivative implicitly, right? That's what the problem says. So take the derivative implicitly and we find 2x plus the derivative of xy is product rule. Derivative of x times y plus x times the derivative of y. Plus the derivative of some stuff squared is 2 times my stuff times, 2 times my stuff times the derivative of my stuff equal to 0. Now, part of me is tempted to just set y prime equal to 0 right now. Right? You could solve. So I don't think it's in our. I don't think we get anything by solving for y prime. Right? You could solve for y prime, like keep these on the same side, and say x y prime plus 2y prime equals negative 2x minus y, and then y prime times x plus 2y equals negative 2x minus y, and then y prime equals negative 2x minus y. But if I'm just going to set y prime equals to 0, that's just going to give me, well, I want this to equal 0. So I want negative 2x minus y to equal 0, aka I want y to equal negative 2x. But here's what I really want you guys to see about this problem. I don't think we had to do all that algebra to actually see the thing we needed to see. Instead, I think we could have just said, well, I want the derivative to be 0, so let's plug in 0 for y prime. So I get 2x plus y plus 0 equals 0. Hey, look, I get y equal to negative 2x. That seems a lot easier. So use what you've got, right? If you know you're trying to find where the derivative is 0, plug in 0. Now, you might be saying, well, James, I still haven't found any points. You're right, we haven't. What we do know is that y has to equal negative 2x. But it also has to be a point on this ellipse. So we actually have to plug back in negative 2x for my y's and then solve for x. Yeah, I'm gonna erase all this down here. So if I plug in negative 2x for y, I get x squared plus x times negative 2x plus negative 2x squared equals 27. So x squared minus 2x squared plus 4x squared equals 27. So 1 minus 2 is negative 1 plus 4 is 3. Someone thought about this question and came up with some nice numbers. So I've got 3x squared equals 27. I've got x squared equals 9. I've got x equal to plus or minus 3. So here are the points. The points are going to be, if x is 3, y is going to be negative 2 times 3. And if x is negative 3, y is going to be negative 2 times negative 3. And let's look back at the problem for a second. So the problem didn't actually say you had to say which one's the highest and which one's the lowest. But we should be able to, because we're not blind. We can, I feel like not making like an ableist statement. I'm not trying to make an ableist statement. I'm saying we can look at the points here and say that, well, clearly this one's the highest because 6 is a bigger value than negative 6. So this is your highest point. This is your lowest point. There we go. Yeah, that's kind of a good question. I like that question. Good question. I'm not saying to me good, I'm saying thank you to the person who suggested we do that one because I think it's a good question. All right, let's look at, I think 12 was the next one, which I just took a glance at. I think it was an optimization problem. Or no, I think it was a related rates problem. Let's see. Here's the problem. You are standing on the ground watching a hot air balloon 30 feet above the ground drift away horizontally in the wind at 10 feet per second. Let's draw a picture. So you are standing on the ground watching a hot air balloon 30 feet above the ground. My hot air balloons often look like light bulbs. That's okay. It's 30 feet above the ground. It's drifting away from you at a rate of 10 feet per second. And it's drifting, right? It's moving in the horizontal direction. It's not going up, it's not going down, it's staying at the same altitude of 30 feet above the ground. So before we start answering questions, we should label the things that are changing. So this horizontal distance from me to where the balloon, to the place directly below the balloon is changing. So I'm going to call that x. this diagonal distance from me to the balloon is also changing. I am usually calling my diagonal distances S. This vertical distance is not changing though, it's 30 feet. All right, so here's the first question. And there are two questions. The first question is, how fast is the distance between the balloon and yourself changing when it is 40 feet away from you horizontally? So how fast is the distance S changing when the horizontal distance X is 40 feet? This is definitely a related rates problem. We want to set up an equation. Well, in fact, first we want to write down what's changing, right? So we know that ds dt is what we want to know, and dx dt is the rate of change of the horizontal. It is how fast the balloon is drifting in the horizontal direction. It is 10 feet per second. Okay, second question, or second thing we need to look at. We need an equation relating S and X, or more generally, our non-time variables. So I'm going to have x squared plus 30 squared equals S squared. After that, after you find the, well, I should say, sometimes there's an intermediate step. Sometimes there's too many variables. Like sometimes you want to know how S is changing and you know how X is changing, and there's some third variable that you know nothing about. Sometimes you have to do some algebra to figure out how to get your equation having only the variables you really care about. In this case, it's not an issue. So we go straight to taking the derivative implicitly. Derivative of x squared is 2x times dx dt. Or the derivative of some stuff squared is 2 times our stuff times the derivative of our stuff. The derivative of 30 squared is 0. The derivative of s squared is 2 times our stuff times the derivative of our stuff. And then we should be able to solve for the thing we want to solve for. So we have to plug in what we know. We know that x is 40 feet. So we get 2 times 40 feet. dx dt is 10 feet per second. Equal to 2 times s. So we don't actually know what s is yet, but we can figure it out. If x is 40 and this is 30, what's s have to be? Well, it's a 30-40 triangle, or a 3-4-5 triangle, but all the sides are multiplied by 10. So it's a 30-40-50 triangle. Right? If this side is 30 and this side is 40 at this particular moment, then at this moment, this side has to be 50. A lot of the time, most of the time, when people give you these kind of problems where you've got like a triangle, they usually, not always, but mostly try to make it so the sides happen to be nice integer numbers instead of a Pythagorean triple, like a 3, 4, 5, or a 6, 8, 10, or a 600, 800, 1,000, or a 5, 12, 13, or any 5, 12, 13 times any number you want. Anyway, let's see. I'm going to have 800 divided by 100 equal to ds dt. So ds dt is going to equal 8 feet per second. I know it's feet per second because it's how a length is changing, and my units of distance were feet and my units of time were seconds. But I could also say that this was 40 feet times 10 feet per second. So this was feet squared per second, but then this was dividing by 50 feet. So the feet squared divided by the feet became feet per second. Oh, sorry, my nose is itchy. Okay. Part 2, bonus part. How fast is the angle of elevation changing at that same moment? Okay, well, that's a good question. theta changing at the same moment. At the moment when x is equal to 40 feet and s is equal to 50 feet. Okay, so just like before, well, kind of like before, if you're trying to figure out how fast a thing is changing, right, we want to know what d theta dt is. And we know that dx dt is 10 feet per second. Technically, so I want to point out, we know that dx dt is 10 feet per second no matter where we are in this picture, whether we're at 40 feet or 50 feet or 1,000 feet for x. As on the other hand, we only know that dx dt is equal to 8 feet per second at this one particular moment. We could use that fact. We don't have to though. Oh, sorry, my eyes are like twitching weirdly. I mean, unlike the non-weird times in your eyes, which is like, yeah, but it's really like getting the twitch on. Eye is super twitchy. Okay, let's have to deal with it. So usually if you're trying to find how theta is changing, you know how x is changing, the most typical way of trying to write an equation is to write an equation that involves theta and x and no other variables. So I would really prefer to say that tangent of theta equals 30 over x. I'd actually really prefer to say that cotangent of theta equals x over 30. So I'd rather differentiate x over 30 than 30 over x. In fact, I'd really rather say that 30 times cotangent of theta is equal to x. I seems like it's going to be the nicest. So I'm going to differentiate both sides. I'm going to get 30 times, the derivative of cotangent is negative cosecant squared. Negative cosecant squared of my stuff times the derivative of my stuff equal to the derivative of x, which is the derivative of x. Plug in. We know that dx dt is 10 feet per second. D theta dt is what we're trying to find. And at the moment in question, x is 40, this is 30, this is 50. So cosecant, I know the cosecant is the reciprocal of sine, and then the sine of theta at this moment is 30 over 50, which is 3/5. So I know the cosecant of theta at the moment in question is 5/3. So this left side is going to be 30 times negative 5/3 squared, which I would probably simplify before I divide it over. So let's see what I get. Let's see, 5/3 squared is 25 over 9. So I get, this left side is negative 30 times 25 over 9 times d theta dt equals 10. Let's cancel a 3 here and a 3 here. So I've got 10 times 25, so I've got negative 250 thirds equals d theta dt equals 10. Oh, sorry, my foot just started cramping. So everything's going wrong. My foot's cramping, my eye's twitching. Something else is weird. Oh, it really is cramping though. Sorry. Don't get old. I don't recommend it. All right. That's what every old person always says, like, don't get old. Yeah. My grandpa was always like, it beats the alternative. So, sorry, a little punchy this last day of class here. So I got 10, and I'm going to multiply by negative 3 over 250. So I get, let's see, the 10 cancels with the 10 there. So my d theta dt is a negative 3 over 25. Does this make sense that it's negative? Well, yes, because as we move from here, say, out to here, the angle of elevation is definitely less. And if something is decreasing, its rate of change should be negative. And in fact, the problem did say how fast is the angle of elevation decreasing. So you can either say the rate of change is negative 3/25, or you can say it's decreasing at positive 3/25. The second thing here is, what are the units? It's a good question. What are the units? Well, if you look back here, we had really tangent of theta equal to 30 feet over x feet, or 30 feet times cotangent of theta equal to x feet, right? Trig functions don't have any units because they're ratios of like things. 30 feet divided by x feet is 30 over x. It's a ratio. So right here, right, I really got 30 feet times this times d theta equals dx dt equals, right, this is 10 feet per second. So when you divide this feet per second by feet, you get something per second. You get blank per second. What do you get? Your angle is changing at negative 3/25 degrees per second? Radians per second. Always radians. Radians don't have a unit, right? There's no dimension associated with radians. That is what we use. Degrees actually are a unit. Let's see. What else? Are there other questions we should look at? I mean, I think the answer to that question is yes. I know you guys can't see them anymore, at least not right easily. So let me just pick something. We could do that. Let's do a graphing problem. Sure. Let's say we're given this. Oh, actually, there was something else I had that I thought was good. I've lost it. I mean, not lost. I've lost the problem I was thinking of. Well, I know what it was. Let's do another optimization problem, and then we can do a graphing problem. This was an optimization problem on a small exam for a 17A class, but I thought it was a good question. Find the point, or points, plural, on the hyperbola. I think it was y squared minus x squared equal to 4. Closest to the point 2, 0. And although we could draw a picture here, I think we should do it without drawing a picture, just because we should be able to do a problem like this without actually having to draw a picture. So here's what we're thinking. There's some point on the hyperbola. It's xy. And we want it to be the closest point to the point 2, 0. I'm trying to not draw the picture because I want to point out you don't have to know what this looks like to be able to solve it. So if you're trying to find the point that's closest to a certain point, what are you actually trying to optimize? You're trying to minimize the distance between the points. So we're trying to minimize the distance, which is equal to, so if I'm going, if the distance between xy and 2, 0, it's the square root of x minus 2 squared plus y minus 0 squared. Now here's a good piece of advice, which I think I've said before, but I'm going to say again. Instead of minimizing the distance, it is always equally correct to minimize the square of the distance. So instead of this, let's look at the distance squared, which is just x minus 2 squared plus y squared. And as we've noted before, we're trying to optimize a thing, and there's 2 variables, and we only want 1 variable. So we need to isolate one of these in our equation. So, right, this is where the picture might be helpful, but I'm still going to say, I know that my point has to be on this ellipse, which means I should be able to solve for x or y here and plug it in here. Which one does it make more sense to solve for? Do I want to solve for x and plug in here, or do I want to solve for y and plug in here? definitely y, right? In fact, I'm not even going to solve for y. I'm going to solve for y squared and plug in for y squared because I've got our y squared. I think this was a really cleverly designed problem. I saw it, I was like, oh yeah, that's a good one. Because it's not too hard to do if you know what you're doing. So solving this for y squared, I get y squared equals x squared plus 4. I'm just going to jam that in right there. So d squared, the distance squared, is x minus 2 squared plus x squared plus 4, right? That's it. Y squared is x squared plus 4, so replace y squared with x squared plus 4. And now we're going to take the derivative. So the derivative here is going to be 2 times x minus 2 plus 2x plus 0. And we're going to set that equal to 0. So let's see what we get. We get 2x minus 4 plus 2x equals 0. We get 4x equals 4. We get x equal to 1. So we're not done for 2 reasons. One, we should check to see that it's actually a minimum. It's probably easier just to use the second derivative test here. So you take the second derivative. So here's my first derivative. My second derivative is 4, which is positive, which means this thing is always concave up, which means if you've got a critical value, it's going to be a minimum. And then the other thing we need to actually do is we need to find the point, or points plural. We found the x coordinate, but we need to find the y coordinate. So if x is 1, well, we can find y, right? Y squared is equal to x squared plus 4. So if x is 1, y squared is 1 squared plus 4. So y squared is 5. So y is plus or minus the square root of 5. So there's actually 2 points, which is not surprising because hyperbolas have a lot of symmetry. The points are 1 comma root 5 and 1 comma negative root 5. If you care to know what the graph actually looks like, hyperbolas always have the same sort of shape. In fact, y equals 1 over x is a hyperbola. It's just oriented in kind of what we think of as an atypical way. Hyperbolas essentially always have 2 asymptotes. It's just usually they're slant asymptotes instead of being vertical and horizontal. For this graph, y squared minus x squared equals to 4. The way I usually graph a hyperbola is I find the intercepts. So here, if x is 0, y can be positive or negative 2. X can't be 0, right? If y can't be 0. If y was 0, you get negative x squared is 4, which isn't going to happen. This looks like this. As x gets larger, right? If x is 1, we just found that y was root 5 and negative root 5. So it kind of does this deal, and then does the same thing to the left. Kind of looks like that. So for the point 2, 0, the point right here at 1 comma root 5 and 1 comma negative root 5, those points are the closest points on the hyperbola to that point, which seems reasonable. But again, right, if you're drawing the picture, I've been like, okay, that's my point 2, 0, and this is my point x, y. We're minimizing the distance between those 2 points. All right, let's do one quick graphing problem. And I say quick because they've already given us all of the derivatives, meaning the first and the second. So here is the graphing problem. The problem is sketch each graph showing all of the things, meaning intercepts, asymptotes, relative extrema, inflection points. So here's my function. My function is 2x squared minus 8 over x minus 1 quantity squared. My first derivative is 16 minus 4x over x minus 1 cubed. And my second derivative is 8x minus 44 over x minus 1 to the 4th. Okay, so let's find all the things. So first the intercepts. So the y-intercept, you're just going to plug in 0 for x. F of 0 is going to be negative 8 over 1, which is negative 8. X-intercepts, you're going to set the whole top equal to 0. I prefer to factor, but whatever you like. 2 times x squared minus 4 equals 0. 2 times x minus 2 times x plus 2 equal to 0. So you get x equal to plus or minus 2. Vertical asymptotes, definitely have vertical asymptote at x equal to 1. Horizontal asymptotes, we may or may not have one. We do here. The degree on top is 2. The degree on the bottom, if you multiply it out, is also 2. You have a 2x squared over a 1x squared if you multiply this out. So you have a y equals 2 as your horizontal asymptote. Leading coefficient on the top divided by the leading coefficient on the bottom. Let's look at the first derivative stuff. Really, when I say first derivative stuff, I mean make a sine chart. I should really say we should find the critical values first. So the critical values, if I set the derivative equal to 0 / undefined, let's see, setting it equal to 0 means the top has to be 0, which means x is 4. Right? You could totally factor out a 4 from the top and write it as 4 times 4 minus x over x minus 1 cubed. You see that, yeah, x equals 4 is a critical value. And x equals 1, although not technically a real critical value because we have a vertical asymptote there, it is still a place where the sign of the first derivative can change, so we definitely should include it. So now I'm going to look at the sine chart for the first derivative. Pick a number larger than 4, like 5. Top is negative, the bottom is positive, so the whole thing's negative. Pick something between 1 and 4, like 2. Top is positive, bottom is positive. Pick something less than 1, like 0. Top is positive, bottom is negative. Cubed is still negative, so positive over negative is negative. So my function is decreasing, increasing, decreasing. This is probably, of all the things we have, this is probably the most useful piece of information for graphing the function. Okay, so we have a relative maximum at 4. So relative maximum at x equal to 4, and y is f of 4, which is 4 comma. If I plug in 4 here, I get 16 times 2 is 32 minus 8 is 24 over 4 minus 1 is 3 squared is 9. 24 over 9 is 8/3. Okay, let me ask you guys, do we have a relative minimum of 1? I've started, when I'm making these sine charts, I started like drawing an open circle at the place where it's undefined, and even drawing like a vertical asymptote. So I know it's going to go like down to negative infinity, and it's going to go up like that. Cool. All right, let's do the second derivative stuff, and then we will graph the thing. So let's see, second derivative is 8x minus 44 over x minus 1 to the 4th. Critical values are going to be 1 again, and whatever makes the top 0 of 8x minus 44 equals 0, 8x equals 44, x equals 44 over 8, which reduces to 11 over 2, or 5.5. Pick a number larger than that, like 10. 80 minus 44 is positive, bottom is positive. Pick a number smaller than that, but bigger than 1, like 2. 60 minus 44 is negative, bottom is still positive. So the whole thing is negative. And pick something less than 1, like 0. I always pick 0 if 0 is an option. Top's negative, bottom is a negative number to the 4th, which is positive, so negative or positive is negative. Concave down, concave down, concave up. So it looks like we have an inflection point at x equal to 11 halves, y equal to f of 11 halves. Which I'm probably not going to find unless someone really, really wants me to. I probably will find it. So let's graph the thing. So let's see what we've got here. We have got y-intercept of -8, x-intercept of ±2. So -8 to -2. And then we have a horizontal asymptote at 2 and a vertical asymptote at 1. And then really the first derivative sine chart is what's going to help us graph the whole thing. We know until we get to 1, it's decreasing. After 1 is increasing. After 4, it's decreasing. So it's decreasing up until 1, increasing afterwards until we get to 4, and then decreasing after 4. So it's all like this. And then I should think about what the y value is at 4. So when I look at 4, the y value is 8/3, which is more than 2. So I have to jump up above my horizontal asymptote and then decrease afterwards. Concave down, and over here at 11/2, the concavity changes from concave down to concave up. And then if you wanted, we could find the y value of 11/2, although it seems not that important. But if you plug in 11/2, you get something stupid. I guess, no, I really don't. I'm fine. You guys convinced me. I didn't say anything, but you convinced me. So if you plug in 11/2, you get 2 times 11/2 squared minus 8 over 11/2 minus 1, which is 9/2 squared. So here's what I've got. Check this out. I know I could cancel a 2 here, but I'm not going to. I'm going to say I've got 242 over 4 minus 8 over 9 over 4. Sorry, 81 over 4. And I'm multiply the top and bottom by 4. So you got 242 minus 32 over 81. And that's going to be 210 over 81, and that's going to be 70 over 27, which is just a little bit smaller than 8/3. Yeah. Interesting. Yeah, because 8/3 would be 72/27. There. So there's your 2 8/3, and then there's your 11/2, comma 70/27. What a dumb number. Okay. So that's all.